Okay. After that rather complicated discussion of quantum numbers and Aufbau diagrams, and I do want you to understand that background information, now we get to simplify the process by using a tool. My favorite tool, actually, the periodic table. So this version of the periodic table takes our lanthanide and actinide series that we were coloring in last week and places them where they actually belong. And so remember, the lanthanide is the top series, and the bottom was the actinide series. You can refer back to your colored-in periodic table that we were working on last week. But these normally are at the bottom of the periodic table, right, where you have the lanthanide series on top, and then the actinides on the bottom. I'm going to assume that you picked up one of the green cardstock periodic tables from the lab, because that is structured in the best way to answer these questions. What you want to do with that is color each block in so you can use that as a tool to help you remember where all the SP, D, and F block is. And so you're going to color in, it doesn't matter what color, but make sure you make a key on it, and that way you'll know that groups 1 and 2 are the S block, along with helium. So pretend like helium is hanging out over here. It's not, but because it's a noble gas, but you know, it goes over here. It's part of the S block, at least. Even though we keep it on the right-hand side of the periodic table, because that's what the reactivity says, and the foundation of the periodic table was reactivity, and remains so. And then we have the P block in pink over here. That's basically groups 13 through 18 on your periodic table, except for helium. And then we have the transition metals in the middle, so that's groups 3 through 12. They are the D block. And then we have the F block, which is going to be on your bottom of the periodic table. Okay? So if an element lands here, that means, right here, whatever element that is, that means that its highest energy level will be 2. Its highest sort of energy level in terms of shape is P, so 2P is its highest orbital. And there will be 3 electrons in the 2P energy level, because you got 1 here, 2 here, 3. Okay, so let's do an example. Gosh, usually I let you guys pick, and we will practice this in class too, so don't sweat it. But I think I'll start with carbon just because it's familiar to us. And so I'm going to mark carbon on here. Yeah, carbon is this one. And so we're going to start from the beginning, just like a game of chutes and ladders. Okay, so here's your starting point every time. And we're going to write down everything we cross until we get to the element we're looking for. So we're in period 1, so that's energy level 1, in the S block. And I have to cross 1, 2, so that means 2 electrons. And then we'll come down here. Now I'm on period 2, still in the S block. I have to cross over 1, 2. So I will fit 2 electrons into the 2s energy level. And then we will hop across, because there's nothing on this line until you get to the P block. We will be on energy level 2 still. The shape is P. And we will go across 1, 2. So this is the same thing that the Aufbau diagram showed. This is called an electron configuration. It shows us where every electron in the system is at. The one piece of information that is missing is the idea that you have 3 boxes in the p orbital and only 1 box in the s orbital. The only way to remember that is to realize that if we went farther, you would have 6 electrons, which you can only do in your Aufbau diagram if every box is full. So you can imagine if we were talking about, what is that, neon? Yep. If we were talking about neon, you would have the same beginning part. The only thing that's different is you'd go 1, 2, 3, 4, 5, 6. So you can have 6 total electrons in 2p. You could also have 6 total in 3p or 4p or 5p because there's always 6 boxes in that area. Okay? So this is the general idea. If we did something a little more complicated, like, for example, iron. Let's do iron. It's in the 6th one here. So 1, 2, 3, 4, 5, 6. This is iron. Okay? Again, we can start all the way back at the beginning. I'm going to erase my electron diagram here. We go back to the beginning, and we cross off everything as we go. Digital periodic tables are handy for this. If you can note on your computer the way that I do, that's a handy way to do it. Anyway, so we start in the beginning, and we go for iron. So this was carbon. This was neon. This will be iron. Starting in the beginning, 1s, there's 2 boxes. 1, 2. 2s has 2 boxes. 2p has 6 boxes. Oops, that's in the wrong spot. Hold on. It is really important to be neat. I am not showing you guys these things for fun. This is how I want you to show your work, okay? So I noticed a lot of us weren't using dimensional analysis. You weren't labeling things with units. These are really the most important skills you get out of chemistry, is attention to detail. And one of the details is that when I write the 6, I'm writing it as a superscript. When I write the energy level, it's a regular number. It's just a 2. Okay? So 2p6, and we come down here, 3s2. And so 3s2, now we're at 3p. And there will be 6. And then we jump down here, we're at 4s2. And then we keep going, and we have arrived at the first d orbital. You'll notice that this is not period 4. We're in period 4, but it is not energy level 4. This is where I told you the d block is the period -1. The energy level is period -1. So that's why we go to 3. This has to do with how the orbitals overlap. I'll show you a picture in a second. So we're in the 3D energy level. 4D is in period 5. 5D is in period 6, and 6D is in period 7. So there is no such thing yet as a 7D electron. There is also no such thing as a 2D electron. There's no answer from Schrödinger's equation that would give us those values. Okay, so 3D, and then we go 1, 2, 3, 4, 5, and 6. This is the complete electron configuration of iron. Now that's a lot to write, and we didn't even do a heavy metal, right? The heavy metals are way down here. So naturally, we want to have a shorthand notation as well. So the shorthand notation will be using the nearest stable element before, using the nearest stable element beforehand. So if we, I'm going to use green because it's not in part of this. So if we go backward, I'm going this way, me going backwards. This is a test of how straight of a line I can draw on a computer. This is the nearest noble gas before, so this is helium, that's neon, so that must be argon. Yeah. I don't actually have the whole periodic table memorized, just the stuff I run into a lot. And noble gases we are going to run into quite a bit at this point because they are the stable atoms that we're going to reference. So, argon ends with 3p6, which means this whole piece right here is the electron configuration of argon. And so I'm going to write that in my noble gas shorthand in brackets, and it's going to signify all those core electrons in iron. Core meaning don't react. They don't do anything. So we don't really need to write them out. And then I will take the valence electrons. Let's do that in blue. So these are the valence electrons. Those are the ones we were talking about last week. Those are the important ones. Those are the ones that do the reactions. Okay, so if I'm allowed to use noble gas shorthand, I wouldn't write out this entire thing. I would find the element I'm looking for, go back to the nearest noble gas before it, not in front of it, before it. And then I could say argon in brackets, 4s2, 3d6, and that's my configuration. You can still use the trick to check and make sure you have the right number, just add them all up. All right, so it will be argon has 18 electrons, its atomic number is 18, plus the 2 from 4s2 plus 6, and we're going to get to 26, and iron has 26 electrons. So that's a nice trick to use to double check your work. Okay, I really recommend coloring in your periodic table with the different colors for each group. It really, really helps to make this a faster process. Then I recommend doing these. Okay, you're going to want to practice writing these, the complete electron configuration, not the noble gas shorthand. Okay, we'll do the shorthand later after you've got the complete. Now I told you I'd show you a picture about why the 3D energy level comes before the 4p, and here's the reason. So as we add more and more electrons in the d orbitals, what we see happen right here is that 4s is lower in energy than 3d is. This has to do with electron repulsion and the fact that we have 26 electrons in iron. Okay, so 4s is always filled first and then the 3d. But there are certain parts of the periodic table where this is not true, where the 4s actually overlaps with the energy level of the d electrons. It only happens in 2 spots. It only happens in group 6 and group 11 because they are very close to being full. So group 6 would have, I'm just going to draw the top of this. So group 6, I'll draw the whole thing. It'll be like this. Oh. Okay. So the P has 3 different shapes, so that's why we just wrote 6 different electrons on there. And then 4s has 2. 3d can have up to 10 electrons. If we're in group 11, so say we're talking about copper as an example, okay, which is in, yeah, it's in group 11. What we're going to do is we're going to see that the next thing to be filled is the 3d before you even get to the p orbitals. As we add more and more electrons into those 5 boxes, right? So copper has 11 electrons because it's in the 11th group. 11 valence electrons, rather. So total it's going to have 29. So if we add them all up, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we're at 20 right now. 21, 22, 23. I missed something. Oh, I missed these ones. Oh, goodness. I wonder if you saw that before I did. That was kind of good. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 27. 28, 29. Okay, almost ran out of space there. So these are our 5 boxes, if you will, our 5 shapes that a d orbital has, one of which is not filled. So as it turns out, as we pair up each box, the energy level of 3d decreases and decreases and decreases until 4s and 3d actually overlap. When that happens, it turns out you'll get a more stable electron configuration, meaning lower in energy, if you take the one from the 4s and you promote it into the 3d. So our valence configuration for copper is going to end up being 4s1, 3d10. Because if you can make a full D shell, that's good news. That only happens in group 11. Group 6 is a similar story, only it's a half full shell. So you'll end up with, for say chromium, you end up with 4s1, 3d5. That's half full. It's stable. Hund's rule says they're all going to spread out and face the same direction. And when that happens, you get a decrease in energy. Okay? So this is not going to get the right answer if you Google it. Or if you do get the right answer, it's presented in the wrong fashion. Because some places will tell you to do 3d5, then 4s1. Other places ignore the fact that a half full or a full d orbital is stable. And so I want you to just follow my videos on this one. This chapter is not a good place to diverge from my recommendations because you will get different answers. And they're all right with a certain lens. But on the lens that we want to be at for Gen Chem, it's important to follow along with these specific videos. Okay, so this is a summary of what we just talked about, as well as the prior slide, which is a summary of noble gas shorthand. The last thing to talk about, the last new piece of information I want to give you, is really interesting to me. I've always been fascinated with magnets ever since I was a little kid, and connects were really popular. I didn't have any, but I got to borrow some, so they're fun to play with. Magnets are strange, right? If you take two magnets facing in the wrong direction, they don't want to go together. But if you flip one of those around, suddenly they are sort of like, boop, attracted to each other, right? So for example, I have these two little magnet toys here. They have some pretty strong magnets in the end of them because you can make all kinds of cool structures. And if I try to push these together in the wrong way, they simply don't go. They try to go around each other. They push each other away. It's like really weird. If you've never played with magnets, I invite you to. It's fun. If I flip one of these around, suddenly they go together easy as can be. So this is the phenomenon of opposites attract. Okay, and this is why we see a reduction in energy. Me pushing these together in the wrong way requires energy to be put into the system. Putting these together gives us energy out of the system. Okay, so that's our connection to chapter 5. So what's happening here is the elements that make up these two magnets in the ends are all aligned along the same magnetic field. Magnetic fields arise from electrons spinning in the same direction. So when we draw our Aufbau diagrams, if we have electrons that are unpaired, then that whatever element that is going to be magnetic. If we have electrons that are paired, that means that the fields will cancel each other and it will not be magnetic. So when things are paired, when things are paired up, all the electrons cancel each other out. We're going to call that diamagnetic. So that would be like a piece of plastic, right? Not magnetic at all. Has no attraction to my magnet or repulsion, no response at all. That's diamagnetic. Things that are magnetic mean that they have unpaired electrons. In science, we call that paramagnetic. Okay, so the one that sounds like paired is not paired. It's kind of, funny that way. Unpaired is paramagnetic. Paired is diamagnetic. Diamagnetic is not affected by magnetic fields. Paramagnetic is affected by magnetic fields, attracted or repelled, depending on the direction. And so that's actually a fun way. Compounds can be magnetic as well, not just elements. We're going to get into chapter 8, how to predict when compounds, simple compounds, are magnetic and when they're not. And this is the basis for that. Here's some practice problems. Some of us are still struggling with chapter 5, which is they're all numbered question 1. Well, question at the top. This is a review from chapter 6, and this is a review from chapter 3. So some good practice. You can come and talk to me in office hours if you feel like you have a really strong grasp on 1 and 3, and 2 is a good review for you to practice for this chapter.